Now, if I really need to formally prove that the convergence is happening, and is it good or is it wrong? So I'll have to look into all the operators. The first one, selection. What selection does is it deletes individual, it dies off individual, so the hypervolume because of selection will only get reduced. You have a population pool, you delete a few individuals, mostly at the extremities, mostly at bad areas, your hypervolume reduces. So this entire hypervolume, it reduces. Hypervolume because it's actually n-dimensional space plotted in one dimension over here. So selection, it reduces. Crossover is depends on what type of crossover you're using, but mostly the hypervolume reduces because of crossover. So you've got two individuals which are parents, and you draw two children in between them, arithmetic crossover. The parents will die off, so the hypervolume from this is reduced to this. So crossover, again, it reduces. Mutation is random movement. Because of mutation, it can increase or decrease, but the mutation rate is extremely small, so the individual barely moves. So even if it increases by a very small margin, in contrast to selection, where some of the individual at the bad areas are not selected at all. So some regions where they are bad individuals only, they completely become laden of population. So selection operator, so hypervolume reduces, and mutation, hypervolume increases. Then of course is my crossover. I'll say that it reduces because I'm using arithmetic crossover. So this is called as exploitation, and this is called as exploration. And in any evolutionary technique, exploration is always smaller than exploitation, so convergence happens. Now, there are two strategies. One says that increase the hypervolume, go into new areas. The other one that says reduce the size of the hypervolume, reduce it up, go to smaller areas. And which one is better? Is exploration better or exploitation is better? Let's find out. Now, currently, the algorithm is more exploitative because selection reduces it dramatically, mutation only increases by a little bit, so it's mostly exploitative. And therefore, if I need to find out whether exploration is better or trying new areas, trying new places, trying distant areas is better, or exploitation is better, just quickly converging somewhere is better, let us draw the two things up. So I'll draw a variant of the algorithm which will be exploitative. Okay, so let's draw a very similar space. So that's the local optima, that's the global optima, and then here you go, and there are some individuals. So a very similar figure. That's important one that needs to survive. Let's try to see how will we make it completely exploitative. So in order to make it completely exploitative, what do I need to do? I need to do a very bad selection. So let's rank all the individual. That's rank 1, that's rank 2, 3, 4, 5. This 5 needs to survive. In fact, this is 5 and this is 6. This 6 needs to survive. And this is 7, 8, 9. Okay, these are not the best ranks, but let's say these are the ranks. Now I need to make this algorithm highly exploitative. So how will I make it highly exploitative? So select best individual too many times and delete most of the rest. So I select 1 3 times, I select 2 times, I select 3 times, I select 4 many times. So my selected individual, they actually become like this, and the rest die off. So this was selected many times, this was selected many times, this was selected many times, and this was selected many times. The rest die off. Of course, they'll produce offsprings and the parent and children will fight, but the offsprings will be all here. And this individual that I want to survive is died off. In the next battle between parent and children also it will not survive, so this dies off. So if I need to make it highly exploitative, I select the best individual too many times. And if I select the best individual too many times, what happens is that I get very early convergence. In one iteration, convergence has already happened. And I converge at local optima. So I converge at the local optima only, and that's bad. So this is good. Early convergence is good, and this is extremely bad. So let's do it the other way around. Let's have an algorithm that is mostly explorative. So again, I have individuals. So I have some individuals, that's the one that I want to survive, and that's what it goes. Now this time this will get selected by luck, or I think that's the individual that I want to survive. So that's the individual that I want to survive, and let's say it survives by luck because I'm mostly selecting all the individuals. To make it mostly explorative, I'm selecting most of the individuals. By trading off, by selecting weaker individuals also a reasonable number of times. So these get selected many times. This gets selected at least once, and let's say these get selected at least once. The poor ones, they still die off. Now after crossover, what do I do is, how do I make it explorative? So to make algorithm explorative, increase mutation rate. And let's see what happens. So these two got selected, only drawing those two individuals. So the crossover children are here. Now I apply mutation with a very high mutation rate. So this flies off here, this flies off here. So you see, it's significantly bad. This gets selected, it produces an offspring, let's say because of a crossover with this somewhere around over here. This flies off. Luckily in this case it was extremely good. They'll start attracting people. So based on this, let's have another generation. And if I do this, so because this has become good, so it will now attract more people and there'll be more individuals here. But what will happen is the crossover individual, let's say, are these, and they'll fly off to any random region. The mutation rate is extremely high. So what really happens is that because the individuals are just flying off, they're going zoom, zoom because of high mutation rate, what happens is no convergence happens, which is bad. However, the chances of getting to global optima are high. Worst case, even if convergence would have happened here, an individual would have suddenly gone zoom and it would have gone in the region where there is global optima, so the individuals are just flying off. So there's a very high chance that the individual flies over and from here and gets into here. There's a very high chance the individuals are just flying off. The only problem is, instead of going like a nice individual here with small steps, it'll fly off again, it'll fly off again, it'll fly off again, and the chances of flying off here are also very high. So you get to the global optima region, but you really don't get convergence into that region. So summarizing, exploration and exploitation are opposite of each other. So high exploration and high exploitation. So if your exploration is high, so high chance of going to global optima, and you got low chance So another way to write down is, so that shows convergence at global optima, likely, and this shows convergence to local optima, more likely, and this is basically slow convergence, and this is high convergence. If you want to make an algorithm highly explorative, you increase mutation rate, increase number of individuals. So it's complicated workspace. So you have too many individuals. So too many individuals convergence is a lot more difficult than a few individuals convergence. So more be the number of individuals for the same time, you'll have to do a lot more work for the convergence. So increasing the number of individuals also delays convergence, which means the algorithm becomes more explorative. And of course, if you want to have high exploitation, then you decrease mutation rate, you go with low number of individuals, the similar thing is with the kind of selection strategy and the selection strategy parameters that you use. Here the selection strategy parameters, they try to select most of the individuals. Here the selection strategy parameters try to only select the best individual large number of times. So if you want to make it highly exploitative, so fitness-based scaling is more suited over here. It selects best individual too many times. Rank-based scaling is more explorative in that sense. It tries to give enough opportunities to every individual, enough fair opportunities to every individual to get selected. That's how you control between exploration and exploitation. So overall, what genetic algorithm does is it tries to start over with a random population, so going to those figures again, it tries to start over with the random population and it slowly goes this thing. There are two forces acting. One is explorative that try to resist convergence, and the other one is exploitative that try to get convergence. The forces that try to get convergence or the exploitation is extremely high, and the ones which tries to resist is exploration is extremely low. Now again the question, which one is better, because there were pros and cons of both of them. And it entirely depends upon how much computation time you have. If you have all the time in the world, you do more exploration, you show very slow convergence. And if you got very little time, you're like, okay, I can take a local optima as well, but I want an extremely fast convergence. So it all depends upon the number of time that you have. So in any algorithm, you look at how much time do you have. Real time, you go with local optima is good enough. You don't have the luxury of a global optima, but the convergence needs to be absolutely fast. A lot of time you will like that, okay, let the algorithm take in as much time as possible. So if I draw the mean fitness or mean cost along with time or generation, I usually have an option of getting an extremely high convergence but converging to local optima. So that's high exploitation. Or I have an option of converging extremely slow and most probably converging into a global optima. In the example, actually, the convergence did not happen, so let me not converge it up fully. So I go into the correct region, but after I going into the correct region, I don't really converge in that region. Or I can trade off between the two of them, and I can still, hopefully by luck, get into the correct region, and so I'm somehow there at a correct optima, and then slowly I'm trying to get deep inside it. So the exploration tries to resist convergence in pursuit of getting into the global optima. It will get into the global optima region, but it will not go deep into the optima. Exploitation says that whichever place you are, just converge out over there. You just converge out over there, and therefore you trade off between the two. Now if you look at this picture again extremely closely, here what happened, I did not want to care about the global optima, local optima, because I was there, all the individuals are at the same optima, whichever got selected. If exploration could delay convergence so that the individuals get into correct optima, fine. Otherwise, if you have all the converge at the local optima and all the individuals are at the local optima, then also there's nothing you can do after this. Now I want to go from here to here. So this is the region where I need small mutation rate. Otherwise, the individuals will take very large step, and even an individual here will take a very large step. So I want them to take small steps so that they go little by little into the minima. On the other hand, if you go over here, this individual needs to take a large step over here to prove its dominance. So it's mostly trying to find out whether it's the same region or not. It's trying to assess the utility of this region. So this is where I need high mutation. So the mutation is larger when the population is spread. As the convergence happens, mutation goes smaller and smaller and smaller and smaller and smaller. And that's why you see, even if my settings are highly exploratory, I slowly come to the correct optima, but from now I actually start reducing my mutation rate and I try to force a convergence to happen. So from now I'll reduce my mutation rate. The individuals will no longer be flying, they'll not be taking large steps, they'll take smaller steps, and I'll try to get into as deeply as possible. That's what I say, that the mutation rate is adaptive. It's high initially when the population is spread. So when the population is spread, the mutation rate is reasonably high over here. And when the population is almost converged, then you reduce the mutation rate so that you go deep inside it. It's exactly the same as the learning rate of the backpropagation algorithm. So initially you take larger steps and then you say that, okay, the learning rate reduces with time when you are at the correct optima and you need to go deep inside it. So the backpropagation algorithm, the similar figure, you initially take large step, but then you slowly start taking smaller steps so that you don't overshoot the minima. The same is with the case of mutation over here. You take large steps over here, but then here your chances of overshooting the minima are high, so you take smaller step. Here you take extremely small step because you absolutely don't want to overshoot the minima. So mostly summarizing, so what really goes on in a genetic algorithm or in any evolutionary algorithm for that matter is, from a large random spread population, I slowly try to converge into the correct global optima over here. And the strategy is the exploration tries to resist convergence enough so that I don't converge at the wrong optima. Otherwise, my convergence would have happened here. So exploration, by selecting far weaker individuals as well and by having a high mutation rate, I made sure that the individuals who are weaker also survive. That's a resistance to convergence into the currently known best optima. And once all my individuals are reasonably close by, then I reduce my mutation rate. Then I want to exploit, then I want to go deep inside the optima. So I reduce my mutation rate, I select only the best individual and try to go as deep as possible by extremely small step sizes. And that is how the algorithm is able to eventually give you great individual. Intuitively, if you look at the new population pool is always fitter than the older one because selection reduces bad individual. Crossover only produces intermediate individual roughly at the same region, and mutation, it can be good or bad. If it's bad, it'll delete those individuals. So the new population is always better than the old one and offers smaller hyper volume because exploitation is more than exploration. So the individuals really go looking near, and they eventually converge at hopefully the global optima. And once that happens, I return my solution, no need to go any further. And so this property that your diversity of the individuals, all your individuals are nearly at the same region, is a check that you can just stop, your convergence has happened. And the result that you get out at that time is the best individual, which will be returned by the evolutionary technique as the best individual stochastically by this kind of a stochastic process.